Since 1977, the Ceiba Lions Club has been a pillar of service and community care on the island. What began with 20 committed members has grown into a legacy of giving back, supporting those in need, and advancing the global mission of Lions Club International. From cultural events to signature service projects like Meals on Wheels and the Food Bank, the Ceiba Lions Club supports the elderly, disabled, and struggling families with compassion and consistency. Their health programs, like annual eye care support and glucose fairs, continue to promote wellness across the island. The club is also a champion for the environment, proudly maintaining an adopted hiking trail and backing local cleanup efforts to protect Ceiba's natural beauty. Several of its members have been honored with the prestigious Melvin Jones Fellow Award for their outstanding dedication, proof that the spirit of service is alive and well on Ceiba. The Ceiba Lions Club, serving with heart for the good of all.
Happy Friday, everyone! Welcome to Liam's Cuisine for another See and Learn night, and I'd also like to give a special shout out to our audience watching from Florida to cheer on their guy John. And you guys who are watching there, you are able to watch this presentation live from Ceiba because of the Ceiba Lions Club, so if we can give a round of applause for them. We'd also like to give a big round of applause for our major sponsors, Public Entity Ceiba, the Caribbean Culture Fund, and the Nature Environment Policy Plan. And of course, a big thank you to all of our sponsors from hotels, restaurants, individuals. We have close to 60 sponsors now, so a big thank you to everyone. And our speaker tonight is generously sponsored by the Cottage Club. So a big round of applause for the Cottage Club. And we do have a raffle going on all month long. Tickets are $5. We are raising funds this year to support Critter Quest 2026, in which case we want to bring more scientists to the island to specifically study the invertebrates of Ceiba, mostly insects. And it should be super fun. We'll have hands-on field projects, even more evening presentations, and activities with school kids. So please consider supporting this raffle. Upcoming events. Tomorrow is a double field project day. So we will start 8 a.m. with tree grafting with Ken Banks, who I do not see yet. Maybe he'll arrive later tonight. But if you are interested, please see Lynn or myself, and there will be a taxi going from the tent up to Spyglass Villa. Then tomorrow night, we are going stargazing with our expert tonight. We'll be doing 2 different stargazing places. We're going to start at Wells Bay, and then we're going to go to the other part of the island in Hell's Gate, and hopefully we will see Saturn. So if you're interested in signing up, let us know. Then our next presentation will be at Hideaway with our tree grafting expert, Ken Banks. And if you attend one of the field projects tomorrow or throughout the month, you will receive a free hat, either a baseball cap or a bucket hat. They're super soft, super nice, and made from recycled materials. So, back by stellar demand, John Della Costa is returning to Saba, and he's bringing the cosmos with him. An astronomer and educator from Southwest Florida, John specializes in some of the universe's most dramatic phenomena, exploding stars and supermassive black holes. When he's not unraveling celestial mysteries, he's operating two of the world's largest telescopes at the National Observatory in southern Arizona. John's deep passion for the universe and his cosmic sense of humor are sure to make your head spin in the best way possible. So get ready for a night under the stars with John.
All right. Hello. Everybody hear me okay? Yes. All right. Wow. I'm back, people. I'm back. First, I'd like to start by thanking the See and Learn Foundation for having me back. I absolutely love Saba, and just thank you guys so much for having me back. Yeah, my name is John Della Costa. I'm an astrophysicist, okay? And there's a little bit of an addendum to that. I no longer work at the world's largest observatory in Arizona. I'll tell you more about that at the end of the talk, okay? So this talk that I've made for you this evening is one that I've been wanting to give for over a decade now. It's been rattling around up here, and I've been lucky enough to be able to present it this evening to you after a long, long time. The goal tonight is to blow your minds, okay? That's my goal. Or at the very least, make you say, what? Okay? So, we're going to have a lot of fun. Please, at any point, stop me if you have any questions or you want me to clarify anything. Happy to do so. We're talking about some crazy things that humans' brains aren't even meant to try to understand. So I'm going to try and bring it down, even for me. I'm trying to bring it down. It's hard to contemplate. Okay, very good. So, first topic, scrub-a-dub density. Oh boy, okay. So, I want to do a little experiment with you this evening, okay? It's actually one of the oldest experiments known to man. One of the first scientists who actually liked experimenting. His name was Galileo Galilei, okay? And he hypothesized that if you drop any two objects from the same height, they will fall to the earth at exactly the same rate and hit the ground at exactly the same time, right? Not with this one. That's a good, you're getting at it, okay? So, I have a hammer here and a feather, okay? I'm going to drop these from roughly the same height. Which one is going to hit the ground first? Yes, sir. The hammer. Very good. That is a great guess. Let's find out, okay? We're going to do some real science here. Okay, now, the feather. Watch out. Okay. 3, 2, 1. Okay, there we go. So, took a while for the feather, right? Let me go grab that real quick. Okay. So, why? Why did the hammer hit the ground first? Was Galileo wrong? What's up?
The hammer has more weight than the feather, so it drops quicker.
That's a great guess. Actually, though, it does not matter what it weighs. You could drop a skyscraper from the same height as this feather, and they should hit the ground at exactly the same time. But they do not, okay? But I'll prove to you why they should. The astronauts on Apollo 15 did this exact same experiment, okay? Where did I put the clicker? Over here. Oh, my goodness. Okay. So, a lot of props. So, feather, hammer, all right? The astronauts on Apollo 15 did this exact same experiment. Which one do you think is going to hit the ground first? On the moon, okay? They did this experiment on the moon. Let's find out. Boom. Hammer in right hand, feather in left. They hit the ground at exactly the same time, okay? Why? Why did that happen? Gravity. No wind resistance, okay? On the moon, there is no air, okay? So the feather and the hammer hit the ground at the same time. On Earth, we have atmosphere that makes it fall slower. If we crunched this feather up into a little ball and made it denser, okay, it would fall faster to the ground. But if it was in space with no air, it would still fall at the same rate, okay? It's all about density, okay? Now, let's try and do this same experiment, but let's use water instead, okay? If I throw these into a pool, which I was really hoping we were next to the pool because I was just going to chuck the hammer right in there, which one of these is going to sink and which one of them is going to float? The hammer. You know your stuff. Let's do it.
The hammer will sink and the feather will float.
Exactly. The hammer will sink and the feather will float. I wish I could have shown you that in the pool over there. Okay? So, I was going to go diving later. Yeah. I brought the snorkel and mask, so yeah. So, it's kind of the same question. Why do big ships float, right? They're massive. This ship is called, it's the largest ship on the ocean today, the largest cruise ship. It's called the Icon of the Seas. And it weighs over 250 million pounds. 250 million pounds. How can something so heavy float? Okay? It's all about density. Density, that's what I'm trying to get at with the hammer people. Come on. Hammer, feather, boats. They're all related somehow. Okay? How? It's the density. Watch out for that iceberg. Starboard. No, okay. So we have density. It's all about density. So why do we care tonight? Why do we care? Saturn. Okay, Saturn. It's the second largest planet in the solar system. It's got a beautiful, beautiful ring. It has a diameter of over 116,000 kilometers. Its volume is massive. 10 to the 14, scientific notation, that means 1 with 14 zeros after it, okay? Kilometers cubed. And its mass is 10 to the 26 kilograms, so that's 1 with 26 zeros after it. So it's really, really, really big, and it's really, really, really heavy, okay? However, it's all about the density. The average density of a ship is less than water. That's why it can float. The average density of Saturn, okay, is less than water if you take the mass and divide it by the volume. So, if you had a big enough bathtub, Saturn would float, okay? Make sure to get behind your rings, all right? That's what I always said. So, this is our first mind-blowing of the evening. Okay, all of our minds are blown. If we had a big enough bathtub, Saturn would float, okay? Amazing, right? Pretty incredible. Thank you. Keep those heads together, though, because we've got more for you, all right? So, next. Okay, we're going to enhance. Anybody ever see CSI? Enhance. We can enhance it more. Enhance. We can do it. Well, we're going to do that even more. So, right there, circled in the sky, is called the Andromeda Galaxy. It is our nearest large galactic neighbor. It's really, really big. It is double the size of our own galaxy, and it has over 1 trillion stars in it, okay? It is 2.5 million light years away, meaning the light that it took to, the time travel, the length of time it took for the light to go from the Andromeda Galaxy to our eyeballs when we look at it, took 2.5 million years, okay? Crazy, crazy. It is the farthest thing that you can see with your naked eye, without any aid, binoculars, telescopes, anything. Hopefully tomorrow night when we go out and observe, meet me there, be square, okay? At 7 o'clock, we're going to try and see the Andromeda Galaxy with our own eyes. The farthest thing you'll ever be able to see with your own eye, okay? Pretty neat. So let's enhance the Andromeda Galaxy. Let's zoom in a little bit, all right? There we go. That's what the Andromeda Galaxy looks like if you could spread out all of its light onto the sky. It's too faint for our eyeballs to see it look that big, but it's actually larger than the full moon. It's actually larger than many full moons on the sky. So it's quite large. Let's zoom in once more, okay? We're zooming in a little bit more. That's the Andromeda Galaxy. zoom in just a tiny bit more. Look at that beauty. Okay, so it's kind of, we call it the sister galaxy to the Milky Way. In about 4 billion years, it's going to collide with our own galaxy. Mark your calendars. Okay, and the Hubble Space Telescope, one of the best observatories ever made, is in space, and it decided to take a couple hundred images of the Andromeda Galaxy on this in this pattern here, okay? And the Andromeda Galaxy is above the atmosphere. Sorry, the Hubble Space Telescope is above the atmosphere, so it doesn't get, the light from this galaxy doesn't get distorted from our atmosphere. The twinkling of the stars don't twinkle when you're in space because the atmosphere jiggles the light around, okay? So Hubble goes up above that to fight against that. It also has very, very precise cameras, so we can zoom in and get the most precise images before James Webb. Now James Webb has the best the resolution, but we're just talking about Hubble here. Okay, so let's zoom in once more. Okay, let's see if this will work, folks. Okay. I'm hoping. Okay, there we go. Can we all see that? We all see that? Oh, man, okay, cool. So these are those images taken by the Hubble Space Telescope of the Andromeda Galaxy. We're going to enhance, okay? We're going to enhance. Just a tiny little smidge. Whoa, okay. How'd that go? A little bit more, okay? Enhance. How's that look? Oh, beautiful, beautiful. Enhance. We're going to keep going all the way this time. Whoa, okay? Look at that. Each one of those little dots that you see, all these little dots, the red ones, the blue ones, those are individual stars inside of the Andromeda Galaxy. And we can see those with the Hubble Space Telescope. Isn't that incredible? And not only can you see stars, but you can see clusters of stars as well. And I don't know if I can find one off the cuff because there are a trillion stars, so we'll be here a while for me looking. But you can kind of see this dark region in the middle here. That's dust in the galaxy itself blocking some of that light. So we can actually see some of these, we can see the stars in the Andromeda Galaxy even though it's 2.5 million light years away.
But they're not really that close to each other.
So that's a great point, Lynn. Amazing point. So, yes, I called you out specifically. So, although they look really, really close together, all of these stars are roughly the same distance as the Earth, or the Sun is, from our nearest neighbor, okay? You have a question? Question?
Do they have any planets inside that?
Oh, we're going to talk about it, okay? We're going to talk about it. If you can be patient for me, we can do it, all right? Now, watch this, okay? All of these stars, even though they look like they're right next to each other, are huge, vast distances away. Very, very, very far. They just look so close because the Andromeda Galaxy is so far away, and it's in a galaxy. So they look close, but they're really not. They're very, very far away. And the whole galaxy itself is like 200,000 light years across, okay? Yeah, the whole galaxy. Say, what? Thank you. We've got it. Okay, so, hold on, let's come back here. And that's a mind blow moment. Okay, I'm contractually obligated to say that every single time, okay? That's a mind blow moment. Okay, so Andromeda Zoom. I love Andromeda Zoom. Ever since the first time I saw it, beautiful, okay? My mind was blown, I hope yours is too. Next. What's the bright idea? Okay, people, what's the bright idea? This is a little GIF of our solar system showing the size scale of the planets, and then it moves to the distance scale of the planets. So what the planets look like in relation in size to each other and the sun. You can see the sun is way larger than the rest of the planets. And also the distances between all of the planets as well. You can see they're really far away, right? Very, very, very far. Wow, look at that. I was saying earlier, Saturn, second largest planet. Get behind those rings, ma'am. Don't forget, okay? Yeah, there we go. Now, the Earth and the Sun, okay? They are 1 astronomical unit away. That's what astronomers define as 93 million miles. Okay, so the sun and the earth, on average, okay, nobody Google that, on average, it's 93 million miles, or 150,000 kilometers, or 150 million kilometers, sorry. So they're really, really far apart. They didn't look too far apart there, but they are really, really far apart. The light from the sun, it takes, how long? 8 minutes. He got it. There you go. I didn't ask, but he answered, and I love it. Very good. So, so the light from the sun takes 8 minutes to get to us. Light is the fastest thing in the entire universe. It travels at over blazing speeds of 3 times 10 to the 8 meters per second, or 300,000 kilometers every single second. Okay, it's the fastest thing in the entire universe. Nothing can go faster, and it takes 8 minutes for the light to get to us from the sun. Okay. Okay, shifting gears a little bit to one of my favorite topics, one of the things that I study, supernovae, okay? So, this is a supernova. This is what is called a core collapse supernova, when the largest stars in the entire universe, when they die, when they're at the end of their lives, they collapse in on themselves, and then they explode into the brightest explosion in the entire universe, called a supernova, okay? This is a core collapse supernova, and it is 10 to the 9 solar luminosities. That's what that L with the little circle and dot means. Okay, so that's 1 billion times brighter than our own sun. Okay, yes? Is that a real footage? No. Oh my goodness, I wish. This is just a simulation. Great question, yeah. I wish that was a real image, although the camera would probably not make it home in that case. Yeah, good question though. So, let us all imagine that, and this can never happen, by the way, but let's imagine that the sun, we're gonna go supernova. The sun is not massive enough. It does not have enough mass, weight, matter inside of it for it to turn into a supernova. So this is never gonna happen. This is just a hypothetical situation, okay? So let's all imagine that the sun explodes into a giant supernova. What would happen here on Earth? What would happen? Nothing. Very good. Nothing for the first 8 minutes. That's a great. We would get barbecued then after. But you wouldn't even have time to, smoke some weenies or whatever, okay? You wouldn't even have time. And here's why. If you were looking at the sun, which you shouldn't, and it exploded, which you wouldn't want to be near it, okay? That explosion would be brighter than a nuclear bomb detonated on your retina, okay? Yes. It would be so bright that a supernova, if you looked at it, would be brighter than a nuclear bomb, a hydrogen bomb being detonated literally on your eyeball, okay? That's how bright supernovae are. That's how much light they emit, okay? There you go. Yes, here it's showing, here it is. That was on a guy's face right there. No, that one has not been done yet. That's just math, okay? So there's a couple, there's a nuclear explosion. I don't know, kind of neat. Pretty bright though, right? So you wouldn't want to be near one of those, or even close enough for it to be on your eyeball. Don't recommend that as well, okay? So, there you go. There's another. And that's a mind blow moment, okay? In this case, literally, all right? But wait, hold your heads together, okay? Hold on. Don't let them explode just yet. Because that isn't the least, that's the least of your problems. The light from the supernova. That's the least of your worries, okay? Here's why. Let's talk a little bit about, question. Yeah, so when if the sun were to explode, which it's not, if the sun were to explode, it would take 8 minutes before that light reached us. So when that nuclear bomb goes off on your retina from the sun exploding, it would take 8 minutes still. It doesn't happen instantly. So we would still think that we had a star up there nice and fine for about 8 minutes, and then it wouldn't be so good for us. Okay, we wouldn't be very good. So, like I said, that light though is not even don't even worry about it, because it's the your smallest problem that day, okay? Your biggest problem are these things called neutrinos, okay? Neutrinos are these subatomic particles that are extremely, extremely small, even smaller than electrons, and they are neutral in their charge. So they don't interact with any other particles really, ever. There's a very, very low chance that a neutrino will ever hit anything that it comes into or tries to pass through. So, how does the sun create energy? Fusion. It's basically a big particle slammer. It slams hydrogen into each other, atoms of hydrogen at the top here. They slam into each other, emit a little bit of energy. That's what we see as light. We get a neutrino out. That's what those little V's are. And then a couple other interactions, but eventually we get to helium, okay? So 2 protons collide, then 2 other protons collide, and then eventually they collide to make helium. This is how the sun creates energy. This is fusion. In this reaction, though, 2 neutrinos are released for every one kind of hydrogen to helium move. You get 2 neutrinos, okay? So, just going to zoom into the sun here. We're going to go deep down into the core. I wouldn't recommend this either, okay? It's pretty hot down there. There's literal fusion going on. Yeah, this is not this is not real footage. That's what's going on at the very center of our sun, okay? So, yeah, exactly. So you wouldn't be getting that one back either. So, how many neutrinos are released from the sun every second? About 10 to the 38 neutrinos, okay? So that's a 1 with 38 zeros after it. Every single second from the sun. Emitted in all directions. If you do the math, and I did, I know some of you are looking at me like I didn't, but I did, okay? I did the math. If you take how many neutrinos are actually reaching Earth, okay, about 100 billion are passing through your thumb and your thumb and your thumb. You get a thumb, you get a thumb. No. Are passing through every single thumb in this room every single second. 100 billion, okay? Or 10 billion. Sorry. 10 billion every single second. But you're not feeling anything through your thumbs, right? Oh no, we had a couple of reactions now. Thumbs are losing left and right. We're losing thumbs. No, so neutrinos they rarely ever interact with anything because they're so small and they have 0 charge, okay? If you ever do get hit by a neutrino, buy a lottery ticket, okay? Because you're gonna win, there's no doubt, okay? It's very, very unlikely. To further let you, to kind of get you in the zone here, I'm gonna break it down even more. If you had 1 light year thick of lead, a lead block. As you know, we use lead to shield from X-rays and other type of radiation when we're getting an X-ray or whatnot. That protects us. If you have 1 light year's worth of lead, if you have a lead block that's 1 light year long, 6 trillion miles, and you let a neutrino pass through that brick, it won't hit any atom inside. It will not hit a single atom. That's how little neutrinos interact with normal matter. Yes? The question was, when would you know if you got hit by a neutrino? It would be a very bad day for you. It depends on where you get hit, though. If it hits you in your thumb, you might feel like it has enough energy, they say, as a baseball, getting hit by a baseball. So if you feel like your thumb kind of get hit like that one day, then you'll know that it was a neutrino, unless you're really good at baseball one day, which you look like you could be. Yeah, question?
Quantum physics, like the dual characteristics of particle, like the wave and the being of particle?
The question was, does this have to do with quantum physics and that mass and energy are related and how particles are also waves and particles at the same time? Kind of. You do take into account some of that math. It's a little bit too complicated to go into here, but just think of it as this particle is extremely small and this also has a 0 net charge, and so it doesn't react with protons, which are positively charged, or neutrons or electrons, which are negatively charged. They don't interact with basically anything. All that being said, okay, in a supernova, 99% of all of the energy in this type of supernova, a core collapse supernova, 99% of the energy is released as neutrinos. 99% of the energy, okay? All little tiny particles that basically don't interact with the star at all and immediately exit. So they actually get to you before the light does, because they get out before the light does. The light can interact with particles. It's kind of weird. I won't go into it. The neutrinos don't. So they actually reach you first. There are so many neutrinos from a star that if you were standing on Earth and the sun were to go supernova, here, I haven't even said it yet. Hold on. Mine's not blown yet. If you were standing on Earth and you got the neutrinos, I'm pre-blowing your minds. So, you would actually die, not from that light being as bright as a nuclear bomb. You would die first from the neutrino radiation. So many neutrinos are emitted from a star that even though they very rarely interact with any matter, so many are emitted during a supernova explosion that if one were at Earth, or one were where the sun was, you would die first of neutrino radiation from so many neutrinos hitting your body. That's how many neutrinos are released from a supernova. They do take up they take up we're actually not sure what the size, it's so small we don't even really know the exact size of it. But there are so many that get released that you get radiation poisoning from the neutrinos first before the light ever touches you, okay? That's a mind blown. Okay. So, I think that's pretty cool that you would actually die first, not from the explosion or the light, but the neutrinos. Question?
Take for neutrinos to travel from the sun to here.
Wonderful question. So, how long do neutrinos take to get from the sun to the Earth? They have mass, okay? We've proven that. Therefore, they cannot travel faster than light. Anything with mass can never travel faster than the speed of light. So, even though they travel slower than the speed of light, it's not by very much, and they get to leave the sun, or whatever star exploded, they get to leave the sun first before the light does, because the light kind of bounces around in there, but the neutrinos just go right out. So they actually get to you first before the light, even though they're traveling faster, or slower than the light itself. You're not even going to see the light. You're gonna be like, huh, that's cool. Huh. It's 8 minutes. It's 8 minutes. Still 8 minutes. Yeah, thank you.
If we're not talking about our solar system, how long does it take light to catch up to neutrinos? Or how far do they travel before the light overtakes the neutrinos?
How long does it take before the neutrinos and the light reach up? I don't know exactly how long it takes. The neutrinos get released first, and eventually the light will come out and overtake it. I'm not sure if that's right next to the star or if it's a light year away. I don't know exactly on that. But ask me and we'll do the math, okay? We'll do some math for you. Question?
Covered by the material that you said earlier, will it be protected then or not?
If you were covered by a light year's worth of lead, would you be protected first? That's a great question. You probably would, because you're a light year away. The Earth is much less than a light year from the sun. So if you were a light year away, but if you were covered in lead, like an X-ray lead covering, you would be dead still. Yeah, you would die from the radiation. Good idea though. That's a great question. Okay, so next, what do we got? Oh, we're shooting hoops now, folks. Okay, thanks for the basketball. We'll get into it. Okay, so this is an image of the Hubble Ultra Deep Field. This is one of the deepest images ever taken by the Hubble Space Telescope. So the Hubble Space Telescope looked at a little dot on the sky for weeks, months at a time. And it allowed all the light to accumulate, and this is the image that it took. This is equivalent to holding the pinhead up at arm's length, okay? So take a needle pin. If you hold it up at arm's length, the size, the relative angular size of the pin's head is roughly the same area that this image takes up on the sky. Does that make sense? So the point is it's very, very small part of the sky. Let's make it even smaller, okay? Let's zoom in. We're enhancing again. We're going to zoom into this little rectangle, this little box, okay? And see what is there. There we go. So there it is. There's a galaxy. Every single little smudge in this image is a galaxy. Every single little dot. That dot, that dot, that dot, that dot, that dot. They're all galaxies. Billions of light years away. They're all galaxies, okay? This is how we determine how many galaxies are in the entire universe. So we basically take this whole image, that Hubble Ultra Deep Field, and we count. We literally just count all of the little smudges that we see in the sky. They have to be galaxies. There are no stars in this part of the sky, really, that we know. So they're all galaxies. We count every single one, and then we do a little bit of math. We just say, what fraction of the sky are you covering here compared to the rest of the sky? And you multiply whatever you counted by that number. It's a super easy calculation. Question?
I'm looking at the upper left, the red one, the one right next to it. How do you know if that's 1 or 2 or n?
So the question was the galaxy in the top left, the little smudge to the right. How do we know what that is? How should we count that? And that's a great question. We might count that as one galaxy because those two smudges, the red galaxy and the blue smudge, might be interacting. We don't really know. Or it could be one galaxy in and of itself, or it could actually be two galaxies that are merging, but they're farther away than this galaxy. So we're not really sure. Scientists who are smarter than I am know how to parse that. No, impossible. Thank you, sir. Thank you. Get him another round. Okay. So we don't really know. But if we do the math and we calculate a conservative estimate, extremely conservative estimate for the number of galaxies in the entire universe is just about 6 trillion. And that's a small number. That's a small number. And that's in the observable universe. The universe is bigger than the observable universe. But we're just doing what we can see for now, folks, okay? So let's just say there are 6 trillion galaxies in the entire observable universe right now, okay? Now, how many stars are there in a galaxy? We can literally count with the Andromeda zoom. We can go in and count. But we use other techniques like seeing how bright the galaxy is and comparing that to what we know stars' brightness to be and kind of do an average. Or we can get the mass of a galaxy and then we know roughly how much our sun weighs and we kind of average things out to get roughly how many stars are in this galaxy. This galaxy is too far away to count all the individual stars. So we use techniques like that. If you just take an average across most galaxies anywhere in the universe, we like to use the number about 100 billion, okay? There are about 100 billion stars in a galaxy on average, okay? So how many stars is that total? It's a lot, okay? But, and we'll do the math, I promise. So, how many planets are there for each star? Here's what we're getting at. Anybody know? How many planets on average are there for every star? We know that we have 8 planets. Sorry, Pluto people, sorry. We've got 8 planets, okay? We've got 8 planets. But on average, the average number that we think is about 1 to 2 planets per star, okay? So if you calculate the number of galaxies and the numbers of stars in the galaxies, then we can get a rough idea of the number of planets in the entire observable universe, okay? So that's 6 times 10 to the 12 times 10 to the 11 is about 10 to the 24. So there are roughly that many planets in the entire observable universe, okay? We'll get there in a minute. We'll get there in a minute. No spoilers, no spoilers. Okay, so there are a lot of planets out there, but we don't really care about Jupiter. I mean, I like Jupiter, don't get me wrong. No offense to the next guy. Jupiter's cool, but we really care about life, right? We want to know, is there life out there in the rest of the universe? So if we ask how many of those planets are Earth-like? Earth-like. What do we mean by Earth-like? We mean orbiting a star that is similar to our own sun at the proper distance away from the sun, because you don't want it to be too close, because then all the water will boil off, right? And then is roughly the same size as the Earth. That's what we count as Earth-like. So roughly the same size, roughly the same distance as Earth, and orbiting a star similar to our own sun. If we do the math, it's about 1% of all the planets in the universe are Earth-like, okay? So that means there are roughly 10 to the 22 Earth-like planets in the observable universe, okay? That's a lot of Earth-like planets, okay? And we know that one of them has life in them. Think about the possibilities that there are for how many Earths there could be out there with maybe life that doesn't look like our own, but possibly life that looks kind of similar. Maybe there's an island out in alien Caribbean somewhere that's tiny, maybe named Basa or something, you know, something like that. Who knows, right? There could be. Ewoks. Yeah. We're dancing. Well, hopefully. Maybe one day we'll find out. But yeah, so think of all the possibilities. To illustrate just how big that number is, okay? Drum roll, please. All right, drum roll. Okay. Basketball, I got it. Thank you, Lynn. Okay, we've got the basketball here. If we make all of those possible planets into basketballs, let's take some guesses, folks. How much volume would it take up? How much volume would it take up? More than a Volkswagen? If you had that many basketballs, what's the volume that it would be? 6 light years of lead. Not quite. Saba, filling up the entire island of Saba. That's a wonderful guess. Any other guesses? Solar system. Okay, that's also a good guess. 1 Earth. Wow. Did you see this talk before? No? What's your guess, sir? A Jupiter. That's a really good guess, too. Well, the answer is it would fill up the entire volume of the planet Earth with basketballs. That's how many Earth-like planets there are in our observable universe. Like I said, those numbers were conservative, and that's just the observable universe. That's not the entire universe, okay? So think about all the possibilities that there are, and that's another mind-blow moment. Yes. Question?
Yeah, not to complicate things, but I know that one of the people are wondering about life in our solar system, the moons around Jupiter and maybe Saturn, I can't remember.
Yep.
But what if you throw those in?
That's a great question. So the question is, what about the possibility of life around other planets in our solar system? For example, like the Europa Clipper, right? Yeah? The Europa Clipper, people, okay, is a mission by NASA that's going to get to the moon, one of the moons of Jupiter called Europa, in the year 2030, roughly. And it was launched last year. It's going to get there in 2030, and it's going to measure Europa. Underneath the icy, thick surface of Europa is a vast, vast ocean of water. A vast ocean where maybe one day we could do some scuba diving. Yeah, you know. Okay, so it's warm underneath the water because Jupiter tugs and pulls on it due to the gravitational pull. So it's actually warm. So we do think that Europa is one of the most likely places to find other types of life that might not be Earth-like that we know of underneath that ice. So Europa Clipper is going to go there and try to find signatures of that life. Now, if you take that into account to this, that only increases that number even more, right? The chances for life. If two possibilities for life, totally distinct from each other, forming in the same solar system. If we were to find life, that's why we're looking for it. If we were to find life, it would change the game. It would basically mean that there is likely life everywhere in the universe. Maybe not like us, maybe even just bacteria, but it would mean that there's life everywhere in the universe. That's why we're looking so hard. Not only just in our solar system, but in solar systems around the rest of the galaxy, too. Okay, let's move on. All right, this is the last one. I have a couple of bonuses, okay? Doing okay on time? Ah, beautiful. I got the okay symbol. All right, so one of my other passions are black holes, okay? Black holes are these very, very dense objects that suck everything into them. If you were to go in, you'd never get out. They have so much gravitation that if light goes in, it can't even escape. And light is the fastest thing in the universe. That's why we call them black holes. They're black. They look black because all the light goes in and it never leaves, okay? So, just to give you an example of what kind of densities you'd need, in order for the Earth to turn into a black hole, you would have to shrink the entire Earth down to the size of a peanut. You'd have to crush everything. Your friends, your family, don't do it. But you'd have to crush the entire world down to the size of a peanut, and then it would turn into a black hole, okay? So that's the kind of densities that we're talking about here. Now, black holes are pretty much everywhere in the universe. They're formed when giant stars explode and die. They leave behind black holes, okay? This is the gravitational well potential of the sun and increasing mass. Black holes have a very, very deep gravitational well. This is the fabric of space-time being warped by black holes, okay? They get warped a lot, all right, because they have a lot of mass, and they're very, very dense, all right? So, out there in the universe, oh, there's another good picture for you. Yeah, they just have this basically infinite gravitational well that if you go into, you're never getting out, even if you travel at the speed of light, which you can't. I'm so sorry. No possibility. Yeah. Okay. So, out there in the universe, there are black holes pretty much. The nearest one to us is about 1,000 light years, but they're everywhere. In the center of every galaxy, we believe there to be a black hole. All right? So they're everywhere. Sometimes, very occasionally, but sometimes those black holes start to orbit each other. They get close enough to where they orbit and orbit and orbit and eventually collide. They merge into one larger black hole. Okay? When they do that, they emit these things called gravitational waves. They've been pretty popular in the news in the last roughly decade, gravitational waves. Einstein predicted them with his theory of relativity. We finally detected them in 2015. They basically make ripples in space-time, like throwing a rock into a pond. A little bit more complicated than that, admittedly. But when black holes spiral in on each other and orbit each other, they make ripples in the fabric of space-time. And that takes energy to do that. Takes energy to do that. So, this is what it looks like when two black holes collide. They orbit around each other, they get faster and faster, the gravitational waves that they emit are really, really big, and then nothing. Okay? So right at that very moment, right there, in the last millisecond, when the black holes are colliding, they're emitting a lot of gravitational waves with extremely high intensity. If you were right next to these black holes, your body would literally be ripped apart from literal space-time waving up and down and ripping every atom in your body apart at once, okay? Don't get near one. That is my advice to you. So, they emit a lot of gravitational waves, which means it takes energy. Question?
The one that is close to our solar system, if that collides with one another, would that hurt people on Earth?
Wonderful question. So there's a black hole that we think is about 1,000 light years away. If there was another black hole right next to it, which there isn't, luckily, and they were to collide, what would happen to us? It's 1,000 light years away. You would actually only need to be about 1 AU, so the distance from the Earth to the sun, to basically not feel anything. So you can get not that far away, and you'll be totally fine. So 1,000 light years is way far enough for you to be fine, young man. Great question. Okay, so it emits a lot of energy through gravitational waves when they do this. Okay? Oh, question.
Stars go into black holes?
Stars can go into black holes. That's one of the things that I study. The black holes at the very centers of galaxies. Stars sometimes go and get eaten by those black holes, and we can actually detect that. It's pretty neat. That was actually a little bit about what my last talk was. Last time I was here on SEBA. So, yeah, we'll talk more about that later. It's a lot of fun. So this is, again, another image, a little GIF of the two black holes, gravitational wells, colliding in on each other. You can see how quickly this happens. Okay? Right when they collide, look at the gravitational waves that they emit. There's this big, giant peak right there. That massive peak, okay, it emits an immense amount of gravitational waves, and it takes a lot of energy. If you look at the black hole mass before and after the two black holes collide, okay, before one of these black holes was 35 solar masses. That's how many, that's one solar mass is how much the sun weighs. That's how we do it in astronomy. We measure it in solar masses. The other black hole was 30 solar masses. If they were to combine and collide, you would expect them to end up at 65 solar masses. But they do not. They actually are slightly less massive when they eventually merge. We miss about 3 solar masses. 3 solar masses. That's a lot of energy. All of that energy is emitted as gravitational waves in that last millisecond, right before they collide. Einstein, baby. It's all about Einstein. Yes, sir?
Are the gravitational waves two-dimensional or three-dimensional?
They're three-dimensional. Yeah. So they don't look like this in a sheet. They get emitted in every direction. Great question. This is just our brains. It's really hard for us to think in 3 dimensions. Yeah, especially me. So, yeah. So, if you use Einstein's very famous equation, we should all know it, E is equal to mc squared. M is the mass, c is the speed of light squared. If you plug that in, you get an energy out. And that's the energy emitted in gravitational waves. Here's the mind-blowing part, people. That amount of energy is equal to the amount of energy released at that moment. It's equal to more. It's actually more than the light coming from every single star in every single galaxy in the entire universe. When those two black holes collide, they emit more energy than all the stars in the entire universe at that last final millisecond. They emit it in gravitational waves, though. This is what the cosmic web looks like. Okay? Okay. It's a little quick. What's your question, sir? We can, those two black holes that collided in that little image there that you saw, they were 1 billion light years away. Yeah. So they basically never get dispersed. Okay? So this is what the cosmic web looks like. Inside of here are all galaxies. These are all basically clusters of galaxies. Like I said, there are 6 trillion galaxies minimum in the entire observable universe. When those two black holes collide, they emit more energy and gravitational waves than every single star in the entire universe at that moment. I don't know about you, but that's a mind-blowing moment. That's a mind-blowing moment to me. That's crazy. How do we come to that conclusion? Because when we take the mass difference between those two black holes and we just plug it into E equals mc squared, we get out more energy in that 0.1 second, or 0.01 second, than with the two black holes. They emit more than that in that last 0.1 second because we can measure that mass difference. And we know roughly how many stars there are in the universe and how many galaxies there are in the universe, and so we can get a rough estimate like that. It's actually a lot more energy than all the stars in the entire observable universe, but yeah. So, mind-blowing. I love, that one's my favorite, and that's why it's at the end. But do I have time for a couple bonuses? Oh my goodness, okay. So, we've got time for a little bit of bonus. So here's some mind-blowing things that they hurt my brain, okay? Hopefully your brains aren't hurting too much right now. Here's one. Now you see me better, okay? The universe is nutty, okay? As you know, okay, watch this. I'm going to do another experiment for you. How big do I seem when I'm standing right here versus over here, okay? Do I look bigger or smaller? I look smaller, right? That happens, right? We all know. It's perspective. The farther away something is, the smaller it appears, okay? But the universe doesn't really like that rule very much. Yes, as galaxies get farther and farther away, as we peer back farther into the universe, galaxies do appear to be getting smaller. They eventually, they keep getting smaller until they hit a certain distance away, at which point they stop growing or getting smaller in size, and then they start getting bigger in size again. Galaxies get larger as you get farther away from them. They grow in their size. How is that possible, right? It's amazing. I find it incredible. The reason is because when we are looking farther back into space-time, it's like a time machine. We're looking back farther and farther to the earliest parts of the universe. In those points of the universe is smaller. The whole universe, because the universe is expanding from the Big Bang, right? The whole universe is smaller, and so the same galaxy in that smaller universe looks bigger. Okay, so once you get to a certain point, the universe starts to shrink too, and then the galaxy in respect to that universe looks bigger. It's all proportion, exactly. So, that's another mind-blowing moment. Yeah, all right. Okay, two more for you, and then we're done. Okay, galaxies collide, question mark. Okay, this is a simulation of the Milky Way galaxy and the Andromeda galaxy colliding. This is going to happen in about 4 billion years. Watch what happens to all of the stars in the galaxies when they eventually collide. Watch what happens. Yeah, this is not to scale. You'll see. Yeah. Due to gravitational interactions, a lot of the stars get flung out into these beautiful tidal tails and tidal shells, we call them. And all of these stars kind of get flung out, and we see this in space. We see galaxies doing this beautiful dance in the sky. I'll play it again. Here's something that blows my mind, okay? When two galaxies, even though they're really, oh, yeah, question. I'm getting there. Watch this. So even though these two galaxies have over, our own Milky Way has 100 billion galaxies. The Andromeda galaxy has a trillion stars. When these two galaxies collide eventually, space is so big, the distance between the stars is so massive that no stars will hit each other. Isn't that amazing? You'd think. None of the stars will actually hit each other. Yeah. They kind of do, right? Yeah, in space, galaxies look a little bit like hurricanes. It's kind of amazing the scale differences between the two. The black holes, great question. So will the black holes collide? The black holes will eventually collide, but it takes billions of years because they have to radiate a lot of energy away as gravitational waves before they get close enough to combine. They will. In some cases they don't, but in most cases they do. We can talk about that later. The whole collision takes 10 billion years. Yeah. For at least our galaxies, for them to be totally one galaxy, the Milk-Dromeda galaxy, if you will. Yeah. 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 So mark your calendar, like I said. So, and that's another, hold on. No! Hold on. Wait. Mind-blowing moment. Yeah. All right. Let's say, what? Thank you. Yeah. Okay. So, final one, and then we'll call it a night and we can ask questions, all right? All right. So, I call this one inflation sensation. In the very, very early universe, the Big Bang happened. The universe started expanding. But before it started expanding at the current rate that we know it, it actually expanded at an incredible rate right before that expansion. So this happened, this thing called inflation, we call it. It happened, this massive, extremely quick inflation of the universe, rapid, rapid expansion. It happened from 0, time equals 0, to time equals 10 to the minus 32. That's 0.000032 zeros seconds after the Big Bang, okay? That's when inflation happened. In that time, the universe went from a point smaller than any point you can possibly think of, smaller than an atom, smaller than an electron, smaller than quarks even. That point in the universe expanded to roughly the size of a beach ball. I'm so sorry I don't have a beach ball with me. I'm so sorry. Expanded to the size of a beach ball. Then inflation stopped, and the normal expansion that we think about happened from beach ball size to now, okay? Inflation was so rapid and so quick that in that time, that 10 to the minus 32 seconds, the universe expanded. So I'll just say this. So when the universe stopped inflation and became the size of a beach ball to now, think about how big the universe has gotten in 13.8 billion years. That's how long the universe has been expanding for. So it went from a beach ball to the size it is now in 13.8 billion years. Divide those two, take a proportion of when the universe was the size of a beach ball to the size it is now. That same proportion, inflation inflated the universe by that same proportion, but not in 13.8 billion years, in 10 to the minus 32 seconds. So the universe expanded at the same proportion that the universe has expanded from the end of inflation to now, to today. That's how insane inflation was in the very, very early universe. That blows my mind. That's another mind-blowing moment. Yeah, okay. So, yes, sir.
Is there any empirical evidence for that inflation theory?
Oh, baby. Okay, so is there any empirical evidence for that inflation? No. But we have evidence that says it should have happened based on the other things that we see in the universe. However, there is an experiment going on down at the South Pole where it's cold, okay? This instrument here, this instrument is one of two. It's called BICEP, okay? BICEP, yeah, like that, baby, yeah. Okay, so BICEP is looking for signatures of inflation in the very early universe, in that light coming from the cosmic microwave background. It hasn't found it yet, but it will, okay? Hopefully, because we're pretty sure it happened, but we don't have any direct evidence. That is what that telescope is looking for. Here's the cool thing. I don't, like I said in the beginning, the addendum to Emily's little message is, I don't work for Kitt Peak National Observatory out in Arizona anymore. I now work for this experiment, okay? So, I am leaving from Saba on Sunday, and I am flying to the South Pole. I get 1 day home to pack, and I am going straight to the South Pole. But I'm not just going for a couple days or a couple weeks. I'm staying there for 13 months. Staying at the South Pole for 13 months, yeah. To study inflation, and with that telescope called BICEP. It's gonna be pretty fun, yeah. So, yeah, can't wait. So, that's it. Any questions? See us tomorrow night. Please come tomorrow night, 7 o'clock. Meet us at the See and Learn tent. And admittedly, it's a little bit difficult to tie Saba in, because I know that's what See and Learn is about. It's tie Saba into what we're talking about. But the universe is everybody's problem, okay? It really is. And that's Saba, by the way. That's Saba. This is a map of the light pollution in the Caribbean. As you can see, Saba is untouched by light pollution. Yeah. So, if you want to see some of the most beautiful skies you've ever seen, you come to this island, okay? Because it's so dark, All right, so come out tomorrow night. We're going to do some awesome stargazing. I have a telescope that fits in my carry-on, so it's not too big. But we're going to do some fun observing tomorrow night at 7 at the See and Learn tent. Please make it out there. And Lynn?
To Save Electric Company?
Oh, yes. So I've been told that the Saba Electric Company, thank you so much, will be shutting off some lights near the road so that we get even darker skies than you'll ever see on Saba, because we'll actually turn some of the lights off on the island. Thank you, the electric company, for doing that. We really appreciate it. And that's another reason why I heart Saba. All right, cool. Any questions about what we've talked about? Any questions? Yeah.
I'm wondering about the origin of the black holes at the center of galaxies.
Sure.
Since they had to, I assume they had to exist before the galaxies exist.
So how did the galaxies at the black holes at the centers of galaxies get there? Yeah, so they weigh billions of times the mass of our own sun. Those two black holes that we are talking about only weigh tens of times the mass of our sun. So how did they get that big? We think in the early universe that there are a couple different theories, but we think that many galaxies will collide, and eventually you'll get so many black holes colliding that they get that big. Or you can get this thing called direct collapse, where you have this massive, massive cloud of gas and dust that is so massive and so dense that all the gravitational attraction brings it down and collapses it directly into a black hole that weighs millions or billions of times the mass of our own sun. So, yeah, it's a lot. So, you go ahead.
For our young people here, can you tell us, at what point in your life did you know you were going to be an astrophysicist?
Okay, so at what point in my life did I know that I was going to be an astrophysicist? There was no set moment when I decided I'm going to do astronomy now. I didn't go to a lot of planetariums. I went to a couple as a kid, but it never really hooked me until the 7th grade. In the 7th grade, for some reason, a light bulb went off in my head, and I said, I want to do astronomy. I like to say it's in my blood. So I don't have a really cute story, but it was about the 7th grade when I decided that I was going to study astronomy. So, yeah. Question?
Something like a question or something else that you want to know or to learn in life about the universe?
Great question. So, the question is there something that I want to know about the universe that hasn't been discovered yet? Yeah, there are a lot of questions that I want to know. Is there life out there in the universe? I think there's a very high likelihood. That's a lot of basketballs, right? So I think there's a pretty high likelihood, but we don't know for sure. We don't know. Maybe we're special. It's unlikely, but it's possible. So I want to know about that. I want to know how black holes got to the centers of galaxies in the beginning. That's still an open question in astronomy. We have theories, but we don't have any direct evidence for how that happened yet. But we will. Eventually we'll get it. We'll make telescopes big enough, and we'll find out. And there are tons of other questions, which I'm happy to talk to you about after, that I would love the answers to, and some that I'm actively working on myself, like inflation. Did inflation actually happen? I'll be working on that for a year in the South Pole. So, yes, sir.
How are solar systems made?
How are solar systems made? Great question. So, in the very early solar system, in our solar system about 4 billion years ago, there was a big cloud of gas and dust that was left over from another star that died previously. That cloud of gas and dust collapsed in on itself due to gravity and formed a disk. And out of that disk and all that gas and dust, the sun formed, and then all of the planets formed around it. Okay? So they form from big clouds of gas and dust, and they have pictures of new solar systems from radio telescopes being formed, and we can see little balls in there of new planets, baby planets being formed. It's pretty amazing. Maybe we'll show you later if you want. Great question. Great question. Anybody else? Yes? Great question. So why are galaxies mainly disc-shaped and not 3D ball structures? Some are ball structures because of interactions. But most galaxies, they actually form exactly like solar systems do. Okay, so you have this giant cloud of gas and dust that forms it creates a, much like the planets and the sun, it out of that gas and dust, you form stars. Another way is those galaxies collide and collide and collide, and due to gravitational interactions and a lot of math, galaxies tend to form disks due to it kind of squishes, like the Earth. Kind of like how the Earth is a little bit squished because it's spinning, the same thing happens to galaxies. They get smushed because they spin. Okay? Great question. Anybody else? Yes, sir.
What's your favorite part of doing this job?
My favorite part of doing this job? Well, in about a month, it'll be warmth. It will be getting warm. That'll probably be my favorite part. But I think just being able to do something that I love and study something that I love, which I've been very lucky to have the support of my whole family my whole life. So yeah, I just like that I get to do what I love. And now I get to do it at the South Pole. So great question. Yes, sir, you had a question.
You mentioned gravity, due to gravity.
Yes, sir.
Do all solar systems have gravity?
Yes, sir. All solar systems have gravity. Gravity is a universal thing. It's everywhere. Anything with mass,
How do we know that?
anything with matter has gravity. How do we know that? There's this particle that we know of called the Higgs boson. It was discovered in, I don't know the exact year, maybe 2011, 2013, something like that, in CERN, the particle accelerator. And the Higgs boson is actually what gives matter gravity, kind of. It's complicated, but we know it's everywhere. We see it across the entire universe. We know that gravity is there. It's one of the fundamental forces, the 4 fundamental forces that are in the universe, and it governs places that are vast distances away. We can measure how it interacts. Although there's some little tweaks and quirks to it, which we're still trying to figure out today. That's one of the reasons why the James Webb Space Telescope is up, and a bunch of other telescopes are being launched into space and built on the ground. Exactly. Yes, sir.
You mentioned there are 4 fundamental forces and gravity is one. What are the other 3?
So the 4 fundamental forces are gravity, the electromagnetic force, the nuclear strong force, and the nuclear weak force. And we really only, the 2 nuclear forces keep you together, but it's the gravity and the electromagnetic forces that we deal with on a daily basis. Great question. Did you have a question over there?
Oh no, it has already been answered.
Okay, very good.
I have a question.
Yes, ma'am.
Well, maybe I'm not a scientist by any
It's okay.
means, but I think I'm thinking billion light years away.
Yeah.
But it seems like the galaxies or the universe beyond Earth has a lot of energy, and on Earth we talk about a lot of clean energy. If only we could find a way to connect that energy for us, it'd be really cool.
Yeah, how can we harness some of that energy? And you know,
Power plants and all
yeah,
these.
believe it or not, we are trying. So in the core of the sun, we've got fusion going on, right? You slam atoms together, they make heavier atoms, they also emit a little bit of light. We are trying to build nuclear fusion reactors here on Earth to create little mini stars here on Earth. If we are able to do that, and there are thousands of scientists across the planet that are working on this every single day, I bet it'll happen within, hopefully, my lifetime. But if we're able to do that, fusion is so efficient that you'll never need any other energy if we can figure out fusion. You'll never need any other energy. It's cheap because it just uses hydrogen. Hydrogen's cheap. It's everywhere. It's the most abundant element in the entire universe. And if we can harness that fusion energy, you never need anything else. It's beautiful. But it's going to take a while to get there, so don't hold your breath. Yeah, that would be fun. That would be fun. Yes, sir.
What are the complications for fusion right now?
The complications for fusion are, it's really, really hot. It's really, really, really hot. In order to contain such a hot plasma of gas, it has to be held in by electromagnetic fields. So electric fields and magnetic fields that keep that plasma from touching any walls, because fusion creates so much energy that it would melt any material that we have on Earth, any atom, it would just vaporize. So we have to keep it suspended in magnetic fields in order for us to be able to try and heat it enough and squeeze it enough to fuse together. Great question. Yeah?
Is the universe gonna grow forever, or is it also possible that there's gonna be an
Now you're asking me some controversial questions, okay? Is the universe going to keep expanding forever, or will it eventually collapse in on itself? The universe, we used to think that the universe started from a point, expanded out, but eventually started slowing down because of gravity. Gravity pulled the universe back in, and eventually we thought it was going to collapse in on itself and create the big crunch, we call it, okay? However, back in 1997, 1998, astronomers discovered that the universe is not slowing down in its expansion. It's not even keeping the expansion rate at the same pace. It's actually accelerating in its expansion, the entire universe. And that is due to something called dark energy, okay? And dark energy, we have no idea what it is, but we know that's the thing that we call the force that's accelerating the universe apart, okay? So the universe will never come back in on itself, and it will likely keep expanding and accelerating forever until eventually the universe expands so much that there are no more galaxies in the sky because they've accelerated away from us. And so we're actually living in quite a unique era in the universe where we can see other parts of the universe. Imagine in, 50 billion years or 100 billion years, there might not be any galaxies in the sky. Those astronomers in 50 billion years will be in the dark. So we're actually very lucky that we're living 13.8 billion years into the universe's history, so where we can measure these things about the universe, because that's how we study the universe, is by looking at the galaxies within it. So those astronomers won't be able to study the universe like we do today. Yes, sir?
So in 50 billion years, will we be able to see other stars in our galaxy?
In 50 billion years, will we be able to see other stars in our galaxy? The answer is yes. But most of the stars that you know and love will be gone. The only stars that will be left in 50 billion years are red dwarfs, really, really tiny stars that aren't very hot and are emitting mostly red light. So the sky will be just, it won't be that bright from the galaxy anymore, but it will be a reddish hue. So, yeah, great question. Anybody else? Doing on time? Okay. Thank you guys so much. Thank you. Thank you. Thank you.
That mind-blowing presentation.
Say what? We invite you guys to stay for dinner if you want, support our sponsor. Thank you all for coming, and we hope you'll join us tomorrow night for his stargazing activity. Thank you, and have a good night, everyone.